Are people familiar with FPGAs?
I have a basic idea of what they are.
Okay, well, I have the Altera development kit, which is now Intel. I have a Xilinx development kit. I have a couple development kits, and I was kind of rooting around on C Studio, and they had a kit for $5. So I figured it came from China, so I figured we'd try it. And lo and behold, 15 days later, I get this board, which appears to be, I think it's a Xilinx clone, but for $5, okay. And it's a, let's see, it's a reasonably, an FPGA is basically, it's a flash programmable piece of hardware, and there are cells which can be programmed from a flash memory to route signals in a particular way. So you have generally a whole bunch of inputs, some gates, some flip-flops, and you can configure that into anything you want. And then you can connect that to any other of the devices, and then you often have some peripherals and some drivers, and so you basically have a configurable piece of hardware. And if you the Raspberry Pi SOS chip is, you can actually download the gate array files for that. Most hardware, digital hardware, is sort of done on gate arrays at this point, programmable logic arrays. And you can get ones that have, they're expensive, but you can get ones that have hundreds of thousands of gates. And so you can configure and test your entire CPU. And a bunch of the stuff, a bunch of the hardware on the ESP 32s, particularly the low power unit, is clearly was prototyped with an FPGA. Just it smells that way to me. So this $5 chip has 1,152 logical units, which are counters, flip-flops. It's got 864 flip-flops. It's got 72 kilobytes of kilobits of RAM. It's got a flash memory. It's got a phase lock loop. It's got a JTAG downloader, and it has 64 megabits of PS RAM, which for $5 is not a bad little combination. It's I haven't pushed it speed-wise. It'll probably do, a couple hundred megahertz would be my guess. But you can configure. It only has one oscillator and a couple of phase lock loops, but you can configure an oscillator, configure countdown circuits, and sort of build all of your logic. It comes in a, well, I'll show you the board. That's the board. Let's say for $5, I was quite happy. The documentation is kind of mostly in Chinese, and it takes you've got to have a little bit of patience to get it running. I first tried to get it running under Linux and didn't have the right device drivers, and finally moved it back down to Windows and got everything to work fine. I've been talking to the GW1N, who's the manufacturer of the chip, and reported on my trouble, and they at least paid lip service to me, which is more than some people do. So it's, but I've successfully got it running under under Windows, and it has an LED connector, and can actually run a 800 by 450 LCD display, which if you do some digging around, you can actually find the code to do that. So it's the chips themselves from Mauser are like $5 a piece in small quantity. So for the entire board, that's not a bad, not bad at all. Let's see.
Is that for the chips or for the board you just showed us?
I got the entire board for $5.
Oh, really?
Yeah. The entire board, including the LCD connector. I got everything for $5, $5.60 something. And it's got an LCD connector, and it's got probably 30 I/O pins. It's it's got some oomph to it.
So what is the programming environment for that?
Well, I was going to try and show you. I'm going to bring up a separate screen. Verilog is a language which is disappeared, which you program in, and it's a C-like language. You have modules. An oscillator is a module. A flip-flop is a counter is a module. One of the modules is a FIFO, so you can set up a 1K by 16 FIFO with the memory on it. And then you can set up a module being a I2C interface. So you all the modules link together in a C-esque type manner. Let's say this. In a C-like manner, and you've got I'd like this to come up. So you everything links together in a so you bring in the example I'm going to try and bring up is a counter. Okay.
Oh, cool. We got it.
We're getting somewhere. Now, okay, let's see. This is an 8-bit counter. And this is the code for the 8-bit counter. The it's defined as a module. The outputs are the C out. The data, these are the sort of interfaces. Some of them are output, some of them are input, some of them are internal registers. The command is, if the load goes high, then load whatever's on the data pins, and there's an 8-bit data pin port into the output. If the load is low, then C out, then increment the counter. That's all that says. So this creates an 8-bit counter, which is a relatively simple example. If I now okay, it's already synthesized. I've got a okay. This is the automatically generated schematic of what of that program that I just showed you. So you can go in. These are the okay. You can these are the various elements. You have a these are the primitives. You have the counters implemented by an adder. The adder then cycles back on itself. You have a what they call a floor planner, which allows you to assign a port to an I/O pin, essentially. So this is the package. This is the view of the package that I have, which is a 48-pin package. I can essentially assign any data pin to any one of those pins. It's a little trickier than that, and sometimes it doesn't have enough highways to route stuff. But these are the logical cells on the thing, and you can specify I want this logical cell here to do this function, so you can kind of optimize it for timing, and then you can. It comes in much larger packages. This is the teeniest package.
Nick, the screen's not actually changing or updating. Oh,
okay.
Now something's happening.
Okay. Yeah. Okay. There. Yeah. Okay. So it's let's see.
Why don't you go full screen? Maybe it'll show more.
Yeah. Let's see.
The square box at the top.
Yeah. Yeah. It's okay. So that okay.
We can see a lot more there.
Okay. Good. Okay. So you've got a floor plan editor, and you've got a timing constraint editor, so you can optimize various timing paths. And I say it should do. My guess is it would do. The base clock in there, I think, is 150 megahertz. It'll do better than that, and it's got some phase lock loops that do the countdown for you. You synthesize the thing, which creates the internal, which does all of the internal routing for you, and okay. If I plug the device in, well, I don't. It's not necessary, but you simply hit program, and it flashes the device. And hey presto, you've got whatever logic you specify, and it's it's all based on this very simple, and I can do things. I could say if load is less than 10, then don't load. Continue to count. You can do. You're basically just you're building your logic just like C code, but C code that runs at 150 megahertz or better. You've got a what do they do with the chip? Okay, there it is. Okay, if I plug the board in, okay, plug that in, turn that one on.
It looks like Pascal.
Yeah, it's kind of a generic program languagey thing. So if I hit run, okay, program device. Yeah, it's program the device, and it just programmed the device, and I now have an 8-bit counter, which I built, in it's programmed. It gave me an error. I'm not sure what I did, but you get the general point. And then it has a JTAG probe, which allows you to single step through it, look at any pins, look at what they're doing. So it's quite a reasonable environment.
Is this editor free?
Yes. It's when I contacted the company because I've been talking to them about doing a YouTube video. It's a Chinese company, and they're clearly all Chinese, and so they were YouTube video, very good. I can I have a slight advantage. I can read a tiny bit of Chinese, and so it's but they're going to get me the updates for the Linux package because I'm less than completely ecstatic running. Okay, let's see, where am I? Running Windows, but it works. So this language is pretty sophisticated. It takes a while. There are lots of courses on it. it's like any other programming language. It's a pain in the ass. But you've got these are it's downloading what they call the IP core, and these are all of the modules that you can bring into that particular thing. So you can bring in this particular unit doesn't have a DSP. Most of them, it does do FFTs, but most of them have built-in hardware multiplies. You've got all sorts of I2C. You've got you can sort of drop in. There's an I2C interface. If I click OK, it will drop that into the program, and then I can just connect it up. I have to sort of define some things, and it takes a little bit of effort, but so let me bring up a more complicated project.
So I have a question.
Sure.
It looks, is that like a graphic designer? Can you go in there and like wire it up like you would?
No, it's not designed so you can't do the I want to connect this to this. The point of the schematic view. Let me bring up this particular one. Okay, this is a fairly complicated LCD driver that runs on the board. This is the schematic view of the thing, and it's okay, full screen that. It's a fairly sophisticated piece of digital logic to run the LCDs. It has clocks. It has RAM, so you can download. It's running an 800 by 480 LCD. You can download. It's got internal memory which stores whatever you download to it. So it's basically a complete LCD driver. It's basically a complete CPU that runs the LCD. The interface is just a standard 8-bit. It looks like you can make it look like anything you want. So it's there are. I've got the Altera. I've got the Xilinx. I've got this. This just happens to be a cheap and simple one to use, and you can drop this little thing into in anywhere. It's obviously considerably faster than a CPU, and it's hardware. So it's a very powerful piece of hardware for $5. And what I have a particular project. There's a piece of equipment called a gamma ray spectroscopy unit, which looks at the emissions when you bombard something with X-rays or gamma rays. And it has what's called a scintillation crystal, which is a specially prepared plastic crystal. When the gamma rays or the X-rays hit the crystal, it emits a photon of light, which you pick up by a photomultiplier. The photons, you're picking up single photons in the photomultiplier, and the energy of the particular photon gives you an indication of what the material is. So I have a 2-inch scintillation crystal, which is for a couple $100, and I have a 12-inch scintillation crystal from a decommissioned, we won't say what it is, which is worth more than I am. And you're getting pulses from the photomultiplier that are on the order of 10 nanoseconds. So I have a high-speed A to D converter. 8 bits, 125 megahertz that runs into the FPGA. The FPGA looks at the data coming in, says if it's above a certain threshold, then do an integration, which simply continually adds the data, the height of the data pulse until the pulse goes away. So the data is, you get the area under the curve for that particular pulse. And then it puts that data into the 2-port RAM, which can be addressed via, it's a FIFO arrangement, so you can address the data from an I2C port, because you don't get many events. It takes a long time to work out what the it's basically a tricorder, what the tricorder is seeing, but you've got data coming in at 125 megahertz from the A to D converter, and that's way too fast for any CPU, any normal CPU to be able to handle. So I'm using this to basically take the data, determine if it's interesting data, and then store it in a FIFO, which can be clocked out at I2C speeds. So that's what I'm doing with it. And I say, it's I'm quite happy now. I've got the thing working. The quiescent on this thing is about 10 microamps. You wake it up, and you can configure. This is the smallest unit they make. The larger units have they're on the order of $20-30, and they have 10,000-20,000 logic units in it, and you can do an incredible amount on those. So that's sort of a quick walkthrough. Now, questions.
I have a question. Nick, you mentioned something about the Raspberry Pi really early on, that it had some connection to FPGAs, or was...
The Raspberry Pi SOS, which is the graphics chip, you can actually get the FPGA code. That was all prototyped on an FPGA.
I see.
And there are Raspberry Pi versions which come with FPGAs. I'm toying with the actual FPGA. It's like a 48-pin. I'm toying with doing a PC board that will throw this on the bottom of an ESP32 module, so that you could do fairly sophisticated high-speed logic functions on the ESP and then move the data out. I haven't haven't decided to do that, and it would involve digging into the hardware a little bit more than I've done at the moment. So I'm let's see, just a minute. I'm not sure where they are. I've got this is a high-speed Altera board, which has an A to D 150 megahertz D to A converter. This will put out sine waves at a data rate of 150 megahertz, which puts out a 10 megahertz pretty pure sine wave. I've got a bunch of other kits like that. I've been playing with DLPs, and this is a DLP projector on a TI board, and I'm playing with driving the DLP projector directly from an FPGA. That's generally how it's done, because some of the things I'm working on require sort of fixed patterns that are loaded out to the DLP projector. I have more than a few DLP projectors. So it's you could buy one of the large arrays and actually put together your own ARM chip. The code is available to do that, and it would run pretty much real speed. Maybe half speed, but you could at least proof the logic.
I may have missed it, Nick. Where did you get the software to do the compilation?
I downloaded it from their website.
So it's free from them?
Free.
Wow. That's always been the big issue with this stuff, doing it at home. It's been the price of the software.
The files from the official website, I think there's a where is it? There's a way to get them. It requires a pass key, a standard. As I say, I just requested one, loaded it up. Nobody apparently programs these damn things in Linux, and so I spent a day and a half fighting around with the Linux stuff, and it just.
I wonder if it'll run in wine.
I wouldn't. It might. It's.
Oh, you need a USB connection, don't you?
Yeah, and
it won't work in wine.
Yeah, and it's got to be the right driver. And I've talked to the manufacturer and said, you don't have the right driver, and they said, oh yeah, we know about that. It's like 2 days, trying to work out. I got it. So it's they are aware of the problem and promised me a fix that if I do a sort of an introductory video, that I'm happier in a Linux environment than I am in a Windows environment.
Yeah, so am I.
But I think it's as much for security reasons. Most of the stuff is programmed in Windows because the modules are the modules are considered intellectual property, and they get kind of protective of them. So it's I mean, you can't buy a TTL gate for $5. You get this is okay. Let's see. This is the code for their FIFO, which is encrypted, and all the manufacturers do that. This is the top level program that sets up the SPRAM, runs the LCD, and the various things below it are the modules. This runs on that $5 board. This is pretty intense. There's a lot of stuff here. I haven't gone through it line by line, and but it's got a phase lock loop that locks onto the clock. Locks onto the clock frequency, counts down to whatever they drive the LCD at. So it is to have that level of power on a and there are if you want to spend $20, there are where is it? Somewhere around here. There's a $20 board which has basically an uncountable number of elements on it, and it has a complete camera interface and an LCD interface. So you could it's probably nigh close to a ESP 8266 in terms of power, and it's $20. Now there's a lot of programming on the to get it to do what a 266 does, but you just basically put together your own pipeline.
So I'm curious about the clocking. That module you showed us, you defined the inputs and outputs and so on. Yep. And as I'm guessing that it's pretty much asynchronous. I mean, it's entirely driven by signals showing up. Or is there something behind the scenes that's orchestrating the when the that you showed us that if statement?
Yeah. I'll go back to that.
Is there? Yeah. So there's like maybe a clock edge, and there's some kind of rule that says this is happening on the rising edge of the clock, or
I mean, it's what you see. What you see there is if the load is low, then load the data. If the load is high, then every time you get a clock pulse, increment the data by the clock pulse.
Yeah, I noticed the line just above that. It says always at pause edge.
Oh yeah, this sets the, you can set clock edge to be positive edge, negative edge. You can
Right. Okay.
Always on the clock edge, so that everything below that is always done on a clock edge. You could do synchronous, you can do asynchronous.
Can you create kind of second order clocks? I mean, is there anything? There's nothing to keep you from like putting in a toggle flip flop and having a clock running at half speed.
No.
And then just tying that into another module.
Yep. I mean, you can drop in I can take this module here and drop it into another module that does something else. Yeah, there's no. These are all you have only one phase lock loop, which will take, and I think it's 150 megahertz master clock, and count it down to whatever sub frequency you want. So you can lock it at 1/100th of the phase of the master clock frequency. The more sophisticated units, which are like $8-9, these are expensive things. Those have 8 or 9 phase lock loops, so you can have any number. You can have multiple clocks running at different speeds, and you've got stuff to do asynchronous and synchronous locking. So it's only limited by your let's see. I can't really show you the JTAG because I'm kind of not set up to do that in this environment. But you've got a full JTAG debugger. So you can toggle pins and make sure that things are behaving kind of the way you expect them. Not always, but kind of.
So yeah, so via the JTAG, you can effectively get a clock rate that's human speed rather than
yep. And you can go in with a JTAG and simulate the clock. So you can go in with the JTAG and define a clock speed as an input to the JTAG, and it will clock things through for you. You can go in, optimize the timing. You can define whatever pins happen to be convenient for you at the time. I've lost that. So you can define pins any way you want to. There are limitations, and it will, if you there are 4 banks which can be set to different voltages. So you can set a bank to TTL, a bank to 3.3 volts. You can do that kind of logical interface. The more sophisticated, the $7-8 units actually have some 12-bit A to D converters on them, so you can simultaneously move the data into a register on the A to D converter, trigger something, fire something else. These aren't blindingly fast A to D converters, but they're I think they were half megahertz devices. So you can move data through, and you don't have to worry about the Raspberry Pi. How many threads do I have running? What's going on? Is someone going to interrupt me? Everything is you, for better or for worse. You are in charge, and then you can do an I2C or an SPI or whatever interface you want on the to get it into a Raspberry Pi. So it is, or an ESP32, and the idea of sort of really beefing up an ESP32 so you can do some very, very high speed logic without having to worry about this. The ESP32s are pretty good, but where is it? Anyway, the ESP32s are pretty good, but if you want, for things like I've got a bunch of LED arrays, the addressable ones, and you can run those things at close to 20 megahertz. The Raspberry Pis won't even begin to support that kind of speed, but you with one of these you can download the whatever you want to the memory and clock it out, and you don't have to worry about it. It's done, all taken care of for you. And there are in that case there are LED drivers for it. I mean, yeah, LED drivers for the so you've got say for $5 you can't even buy a NAND gate. You know, by the time you order from DigiKey, it'll cost you more than that.
So when you write the code for this, does that generate the schematic view?
Yes.
Okay, but you can't go the other way around.
No.
You will eventually.
Oh yeah, no. I mean, this is free.
Yeah, I know.
You know, I mean, it is, and you know, I really don't have a problem dealing with something that looks like code.
What sort of packages does it come in?
This is in a 48-pin, which is kind of, you know, it's one of those packages with the legs out all of the side. I think there are, you've got projects, add a device. You've got, these are all the packages it comes in.
Yeah, so LQFP is what you're saying.
Yeah, that's what I've got. You know, these are all the packages, so you can select a particular package, and then it comes up with the devices. It will tell you what's available on the device, what family the device is from. These are all the devices they have, which okay, expand that. Okay, the larger packages have these have 16 18 by 18 multipliers, which is I mean you can do blindingly fast FFTs in there, and they've got the FFT is simply a module, so I can't do much of an FFT on this unit, but if I go to IP core, okay, let's see. Come on. Okay, DSP and FFT. It's fairly well documented. I'm not sure that this particular device is probably two. Oh no, okay, that is the FFT module. It'll do a 1024 input FFT. All I do is hit OK, and it will generate that. And I have a $5 FFT. It takes a little while, but
so does this company, they make the chip and the software for programming?
And I think it's a clone of a Xilinx. And you know, they just happen to be very cheap at this point. And this is the FFT code. I've just imported that module into what I'm doing. I could do I mean, this process, I could do a synthesize. It probably won't work. Okay, clean and rerun. Yeah, okay, do that. I don't care. Yeah, okay. It gave me some. There are some parameters I didn't specify, but basically, there's no 18 by 18 multiplier on the small chips. If I'd gone to the $7 chip, it has an 18 by 18 multiplier, so you could do the FFTs. And this chip is frankly somewhat I/O bound at 48 pins. By the time you've got rid of, you know, it's you've got okay, run synthesis first. I mean, anyway, I'm in a bad state here, but you've got 7, you got 8, 16, you've got maybe 20 pins here. That's by the time you've got all the grounds and everything else, that's a fairly large budget of pins. I know the bigger packages are a pain in the ass to deal with. I was interested in this unit because it was such a small package. I mean, it's easy to deal with. It's not like a ball grid array. It's not really fine pitch. I could probably, even though I'm half blind, I could probably solder that thing myself. And I have a vapor phase soldering unit anyway, so I could get that done. So it's generally I'm impressed.
Yeah, it seems like it would make experimentation very, very accessible, and I could imagine folks that have a yearning to like make their own computer could have a party with that thing. You could probably duplicate a 8008 in with that package by itself, couldn't you?
You probably, you probably could. It is. It is, yeah. If there are lots of instances where I want to do a sort of a simple bit of logic, and it may only use up 5% of the devices, but I want a signal to come in, and I want it to invert here and not invert there, and drive this, and have a slight delay there. It's that is a fraction of what this is capable of, but it's cheap and it's simple. And I've used these things. I'm probably building an 8080 on the chip is probably would take me quite a bit of time.
Oh, no, I mentioned I was talking about the precursor to that, the 8008.
Yeah, the 4000.
Really dumb one.
Yeah, the 4004.
Well, not quite that dumb.
Yeah, I mean, it is, and you tend to go to the most extreme uses of these things. It's like somebody opened a Pandora's box. But you've got a little 32-pin package which basically could do most of your discrete logic. Whatever it's whatever you were thinking of doing in TTLs with counters and blah blah, and you want it to run at reasonable speeds, done. If you want a frequency counter, done. It's the frequency counter that'll do 100 megahertz. That's what's sitting here. All I have to do is to increase the if I set these to be 24 bits, then I'll become IO bound. But if I took the load function out, I could increase the outputs to 24 bits, and I have a 24-bit frequency counter. That's a whole bunch of TTL. It's a pain in the ass, and you generally get it wrong on the first iteration anyway. In this case, you got JTAG. You can go in, diddle it, and do whatever you want. Make it do whatever you want. So
how many times can you
20,000
write to it?
20,000.
3,000 times?
20.
Oh, 20,000.
Yep. There are different stages of memory, okay, let's see. There are some functions which you can only write to 2,000 or 3,000 times. Most of them are up in the 20. I think it was 200,000 for the flash memory, and it loads. In this case, it loads from an external flash memory. There's no, the SP RAM is external to this. So it's a sort of a single drop-in chip. Okay, let me get back. Okay, there, that's me. So it's a single drop-in chip that it has a clock output, which is a phase lock loop, an internal oscillator to a phase lock loop. So if you need a 40 megahertz oscillator, you've got one. If you need a 2 megahertz oscillator, you've got one. It's not the most precise. There are basically complete programs to generate a sine wave output. So if you want to make a quick sine wave generator that runs a D to A converter, done. It's I say they're there's somewhat of a learning curve, but that's something that I don't think anyone here is afraid of. And I have one of the I mean, these things here, you could do an ESP32 clearly on one of these, and I've got these are considerably more powerful units, but it's the $20 unit that I got. Where is it? Oh, FPGA. Okay, it's in the FPGA box. This is a $20 unit. Whoa! It has a it'll run a 1K by 1280. It has its own SD card interface, and it has a camera interface. This is a much higher level chip, and hell, that was 20. And even at that, if you only put a couple leads on it, this is a much faster unit. This will probably do 500 megahertz, which I'm not sure I can do. None of my scopes will go up that high. So, it's a that one it's a similar programming environment. They're all just very slightly different, but this plugs in micro USB, JTAG, and the software for this one is also free. It's just one piece of software at a time.
Yeah, I'm looking at it. The $20 one appears to have 20,000 logical units versus the 1,100.
Yep. Which is more than I can handle.
Yeah, that'll keep you busy.
That's that's like crazy talk. So yeah, it's but there are a number of little projects that driving the DLP displays. This is my this is one of my scanning units for plant research. That is camera. This is a DLP projector, so it projects an image out here on the plant, and then the camera. It's multispectral image that comes out here. The camera then scans the image and can diagnose what's wrong with the plant. And the bottom of this is a Raspberry Pi. So this is it's not perfect, but this is a little. I have a couple of these I built. This is an entire entire thing, and using the 20,000 gate one will easily drive the DLP projector and let me do all of the analysis in the Raspberry Pi. So that's I think Steed Studio's out of the $5 boards at the moment, but I think there are some on Amazon, and apparently the company the company has a bunch of them. They kind of touted that they had a whole bunch of the chips. And I know the chips that they're still available on DigiKey, so they're not something that's shorted at the moment. That's my brief introduction to, and it's a learning curve, but might as well learn something.
Very good. Well, thank you, Nick. So does anybody else have something to share? I had something happen this morning that was amusing, and I thought it might be interesting.
Yep. Index
Okay.
of home, piece over.
So, right. So can you see that okay?
Yep.
Is that pretty clear? Okay, so I had this code, and I compiled it, and it was extremely surprising. And here's why. Here is a function call, and here's a function call, and each of these macros expands into function calls, and then here's a function call. And actually in the, I'm sorry, this might be actually an updated version of this file, but I had these three function calls, and this one right here was never being called. And so I disassembled the function inside GDB, and here's the code. And I apologize, I had 4 instances of the crash macro, and there's only one here because it was an earlier version. And you'll notice there's the call to the standby, and there's a call to the active, and there's a call to crash, but there's no call to the function that I was trying to call. And the compiler appeared to have omitted it, and I had to stare at it for quite a while before I finally achieved enlightenment. And I'll show you the code again. Here's the first function, and there's that bottom one. And the compiler has literally skipped compiling this function call. Does anybody see my mistake? Well, here's the correct code. Do you notice a difference?
Yeah.
I left out the case keywords.
Cases, yes.
Yep.
So I had 4 labeled statements, or 4 labels, and a bunch of statements. And it goes to compile the code for this switch, and it says, okay, now I'm going to generate the code for this switch. I'll generate the code for case. Well, I don't have any cases, but I do have a default. And so it only generated the code for the default case because I had momentarily forgotten how to code a switch statement. And it compiles just great because it's a valid label.
Yep.
So switch back to the old one for a second.
Sure.
Yep, I see it now.
Okay, yeah. So you actually do have a default, so that's the only thing that would have ever gotten it called.
Yeah, so it literally, it knows that control, I don't know why it would legally accept these statements hanging in here.
That sounds strange to me. To me, it should cause an error.
But yeah, but you could be making a long jump into one of those statements from somewhere else.
That's right. And so in their wisdom, the designers of the language, for some reason, decided to allow this. And so these statements are absolutely unreachable unless you use a goto or a long jump to get to them.
And I took care of it for you.
There you go. Yeah, but the compiler also, it knew that there were no references to these labels, and so it didn't actually have to generate any code.
It's not going to do the work.
So
it have to. So
it just ground. Yeah, exactly. Why should it put out code that isn't going to get executed?
Yeah.
And the last interesting thing, and you guys might find this to be useful. Here's a little trick that you can put into your. This is C++, by the way. You can put into your GCC source code, and this specifies an optimization level of 0, which is no optimization, except as with many compilers, you can't actually turn off all optimization. So the fact that the compiler doesn't generate code for unreferenced statements is just something that you're going to get, and you just have to live with it. Most people would not notice that, let alone the fact that it had cleverly
I had to stare at it for a while to realize that's what it was, but it's obvious. Said it.
I stared at it for I'm going to say about 10 minutes.
It's taken me longer to get to some of the stupid mistakes I've made.
It was.
That's relatively quick compared to
what
I've done.
I don't know if that makes it more or less embarrassing to say that I worked on compilers for years, and so I was on the other side of these compilers for a long, long time. And but in my defense, I've dealt with. I've used switch statements. That, with language, a lot of languages have this basic type of statement, and their syntax is a little different here and there and the other. And so, it made perfect sense to me to just stick the case values up here without the keyword. But then I got a subtle reminder that was not what I intended. Anyway, that's all I had. Yeah, I found this very interesting, and I think that it'll be fun to. There'll be no doubt folks getting involved with FPGAs after they've seen how easy it is.
And if you need someone to further confuse you, I can provide a little bit of help. There are people who dedicate their life to this. I'm not one of them. I'm just interested in a piece of hardware I can throw in quickly to grab data at 200 megahertz, and that ain't a Raspberry Pi.
Well, I didn't appreciate just how easy they've made it.
Yep.
And also how inexpensive and accessible.
So that programming language, is that kind of universal?
There are two programming languages. There's Verilog, which is what that is, and there's another one that, and they're both standard. Yeah, they're both universal. I mean, you can take that and run that on any device.
Wow.
So you can run it on an Intel or a Xilinx. The GUI is going to be different, but that's but yeah, there are whole libraries full of you can take somewhere. I have the Raspberry Pi silicon on system on the chip code, and I could take that, which is I think written in Verilog, download it to a big enough chip, and actually create the video interface. Presumably, I could create. I think the code for the Raspberry Pi is available. So
wow.
If I wanted to spend $1,000 on one of the big chips, I probably could, it'd take it 48 hours to compile, but you could run, you could make your own Raspberry Pi, your own ARM chip.
That's wild.
And as I say, the ESP32s have the smell. I know that the old Atmel chips were done on FPGAs. They were done as a college project, and all of the old Atmel stuff was all FPGA stuff. And there are compilers that will take the basically the layout that you have in Vlog, and they 6 months later you'll have chips, and that's how all of the Atmel stuff came into being.
Huh.
So weren't they in Norway?
Yes, yeah, it was a University of Oslo project, and they produced,
they monetized it.
Yeah, they monetized it, and they got very wealthy doing it. But yeah, it was done as a 8 bits in. Okay, let's do a barrel shifter and this and that, and flash it up, and hey, we got something good here.